So, in this chapter, we're going to be looking at a new concept called capacitance. And what you see drawn in front of you or illustrated in front of you is a bunch of different devices which exhibit this capacitance. Uh, the devices themselves are called capacitors. You can actually see the word right here. Um, and they come in all kinds of various shapes and sizes. No, these are not flux capacitors from Back to the Future. Capacitors are real things. What are they designed to do? They're designed to store electrical charge. Also, they're designed to store electrical energy in the form of an electric field, which is why this chapter comes after our chapters on Gauss's law, electric field, and also electrical potential. We'll see why that comes to play in this in just a moment. Discovery. I need to take you back a little ways. This is way back when. Up that time, we're talking 1600s. Everybody was trying to make a solution of electricity. The idea here is that you could use an electrostatic generator. In this case, let's say it's producing electrons. And so you'd end up with this negatively charged rod coming in and charging the water as well. And everybody was convinced that you could make a solution of electricity that would somehow stay inside the water. And you might say, well, that's a really strange idea. Why would you ever even consider that? Well, at the time, people were convinced that hot water was just like ordinary water, except that hot water had caloric, this invisible massless substance dissolved in it, and that's what made it hot. And if you took hot water and mixed it with cool water, some of the caloric from the hot water would dissolve in the cool water, and you'd end up with both kind of lukewarm water. And so they were convinced, since hot water was a solution of caloric in water, that you should be able to make a solution of electricity. Well, people tried and tried and tried. The issue so what they would do is they'd run the electrostatic generator. Then when they were done, they would disconnect it from the electrostatic generator. Imagine pulling this wire out. And then somebody who was trained to be an electrician, which had a different meaning back then. Electricians were people who were trained to measure the electrical potential or voltage by touching a particular conductor. In this case, then, the electrician would hold onto the beaker with one hand and then dip their finger on the inside to touch the charged water. And each time they did this, surprisingly enough, nothing happened. And you might say, whoa, why didn't it work? Why couldn't you make the water negative? Well, in reality, they did. But the thing I need to tell you is, and most of you know this already, charge tries to get away from each other. It gets as far away from each other as it possibly can. So where would the negative charge go in this while it was being charged? It would go to the outside edges, just along here and along the sides and along the surface, trying to get as far away as possible. And the moment you disconnected the lead, something interesting would happen. If there were any water molecules present in the room at all, and I need to quickly remind you about water molecules, you've got the two hydrogens, and you've got the oxygen, and I'm drawing this way too large. Well, the oxygen part of it is very electronegative. It becomes slightly negative, delta negative, and the two hydrogens become slightly positive. So what happens? The slightly positive end of this dipole would get attracted over here, and the water molecule would go over here and get attracted to the negative surface. The moment it did that, it would become negatively charged, which then would repel it. And so you've got this little H2O molecule, I won't draw it out again, with a net negative charge now because it picked up one of the electrons there. And it would fly off until it ran into a wall or a ceiling or anything else in the room, where it would drop its charge, and then it could very quickly repeat that. Now you might say, wait, that's a very slow way of losing charge. Well, it happens naturally. Every time you walk across a room, you build up charge, but because of the humidity in the room, those water molecules very quickly dissipate that energy. And we're talking about hundreds of billions, if not trillions, of water molecules per second very quickly discharging you. Now, in a dry winter day, yes, you can build up charge and you won't have enough water molecules to discharge it rapidly enough, which is why you can get a shock on a door. So, what was the big discovery? Well, the discovery was a Leyden jar. And it was actually kind of an accidental discovery. In this lab, you've got the electrostatic generator over here, you've got a conductor going over here, and you've got the container of water. And oh, by the way, Leiden now is right here near Amsterdam, spelled slightly differently now than it was back then. But what was the difference this time? Well, remember, this has been going on. People have been trying to make a solution of electricity for ages. But in this particular experiment, the electrician kept their hand on the outside of the beaker as it was being charged. And as you can see here, he's about to touch the wire. Yeah. So Moisenbroek was a lab, and in this case, you see the assistant there, who's the electrician. When he actually touched the wire this time, he got an incredibly large shock. And you might say, whoa, 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 wait a second. Didn't you just tell us it would all just go away? Yeah, there's something interesting happening here. What was the difference this time? Well, the difference this time is that he was holding it while it was getting charged. And yes, the water became negatively charged just like before. But this time something interesting happened. The glass is an insulator. So what happened? The electrons in the person's hand were repelled, and they would actually go out, down through the arm, down through the shoes of the assistant to the earth and actually escape. Meaning that overall, while it was being charged, the assistant's hand became positively charged. And you might say, yeah, but that positive charge couldn't interact with the negative charge. That's true. But think about what happened next. When it was disconnected, sure enough, the charge on the top here would dissipate very quickly with water molecules. But what about the negative charge at the bottom here where he's holding it? Well, it's being attracted to the positive charge of the assistant's hand, and the positive charge is being attracted to the negative charge here, but they can't get to each other because of the glass barrier. However, as you might have guessed, what would happen when the assistant actually touched the wire? The charge here would very quickly go up the wire, back through the assistant's body, and back to the hand to neutralize this excess or this positive charge here, the deficit of electrons. And yes, suddenly you could store charge as long as you seem to put a hand at the bottom. That was the big discovery. In reality, we soon discovered you didn't need to have water, and you didn't even need to have a hand. All you needed was two conductors separated by an insulator. And this is one of the simplest ones possible. In this case, this is a plastic insulator that fits perfectly between the two metal cans. And this is one of the simplest ones you can make for a Leyden jar. Where in this case you can charge the inside here. This metal ball is connected to this inside metal plate. Let's say we made this one negative, and very quickly then this outside part of it, I can't quite draw enough negative charge, would become positively charged. And this thing would store charge. This was our very first capacitor. Capacitor is the modern name for the Leyden jar, or in other words, the storage device that was accidentally discovered at the University of Leiden. A quick little video on this, just so you can sort of visually see it. I can't remember if there's audio or not, but take a look at it. So in this case, got a Leyden jar, we got a simple bottle. We're going to, again, just put a little piece of foil on the inside here. The foil coating in the inside is our conductor on the inside. That's taking the place of the water that was in the original container. We're connecting that to a metal rod that goes through an insulator. This is how we can charge the inside then, instead of having a wire stuck in there. And then we're going to put a piece of foil on the outside as well. That's being shown here as kind of gold. So here we have a Leyden jar, or basically the same thing as you just saw. Here's a cross section of it. And what we're about to do is connect it to a battery. And we're going to connect the outside to the positive and the inside to the negative. What's going to happen here? Electrons are going to flow out from the negative, and my apologies here, they actually show positive charge moving through the wire. In reality, that would just be electrons moving this way um, out through this thing, electrons leaving the outside, leaving it with a net positive charge on the outside. And as we do that, this thing becomes electrically charged. And because they're opposite charges, it tends to hold the charge in place. And even if you remove the battery, the charge would stay there. Now, if you take that and hook it up now to a light bulb, you can actually run the light bulb. And at this point now, we've got electrons are actually reversing direction. Electrons are now flowing out from this way, from the excess part of the inside, trying to get to the outside of this thing, which has a deficit of electrons. And we end up with this nice flow of charge. So take a look at this, and I need to give you now the mathematical definition of capacitance. So take a look at this. We've got a very simple hollow conducting sphere of radius r, and it has some positive charge q on it. If you remember, the electric field around one of these things, you could use Gauss's law to use it as well, is given by this, where x is how far you're away from the inside of this thing. So the electric field at this point, some distance x, would be given by that. Remember then you could integrate this with respect to distance, and I won't do the integral this time. You could then figure out the potential at that point, and the potential at any point outside of this thing would simply be given by q over 4 pi epsilon naught q. Q over 4 pi epsilon naught x. If you take that then, you can actually find the potential at the surface of this thing. What's the potential at the surface? Well, we just insert the radius for x. And so we end up with this. What happens if we increase the charge on this thing? Well, as we increase Q, what's going to happen to the voltage? The radius of this thing is constant, epsilon naught is constant, pi is constant, 4 is constant. So what you're going to end up with here is if you charge it to Q, you get some particular voltage. If you charge it to 2Q, you get twice that voltage. And you can continue that on, and you'll discover it's a beautiful linear graph. And you're like, yeah, that makes sense. Well, here it is. Here's the definition of capacitance. The capacitance of any object is simply the amount of charge per unit volt, or charge per unit electric potential. And because of the fact that this is a linear relationship, the capacitance of this particular thing is some constant value, which depends on its radius and a few other things, or its radius basically. We'll talk more about how we calculate that later. But for now, just remember this definition. We'll do a look at that again in a moment. Real quick on this, we know the potential is that. Actually, I'm going to derive it here for you. And so it turns out the capacitance of this thing, I forgot I put it on the slide, is simply given by 4 pi epsilon naught r, where r is the radius. Capacitance is a measure of how much charge you can store for a given voltage. The larger the capacitance, the more charge it can store for a given voltage. We try to typically maximize capacitance when we're creating capacitors. For electrical circuits, we try to minimize it. We don't want too much charge stored at any given point. I'll talk more about this later. So the simplest of all capacitors is something called a parallel plate capacitor, where we simply have two conductors, metal plates, separated by some sort of insulator. And we're going to use a fancy name for an insulator in this chapter. It's going to be called a dielectric. And you might say, whoa, why is it called dielectric? Di is two. Well, think about it. Even in an insulator, we can get polarization. So for example, if this is a piece of plastic, inside each little polymer, we'll end up with this side of the polymer becoming slightly positive, this side slightly negative. And so we end up with two charges in it, a dielectric charge, a dipole basically forming inside of this. And there'll be a bunch of them, but their charge here is not free to move if this thing is an insulator. And dielectrics are always insulators. So two conductors of any shape placed near each other without touching. The two conductors are separated by an insulator. The insulator is called the dielectric. So you got the basic ideas. So capacitors come in all shapes and sizes, like I showed in the picture up on top here, but the simplest of all is that parallel lip plate capacitor that we have here. And we already talked about the definition of capacitance. Well, you can also figure out the charge on each capacitor plate if we rearrange this equation. If you solve it for Q, Q is just going to be equal to the capacitance times the potential difference. It's a very simple idea. Where C is, again, defined as capacitance, we haven't talked about the units yet. Officially, the units are coulombs per volt. Well, if you remember, volt is defined as the number of joules per coulomb. And so you could actually rewrite this one for the units. You've got coulombs divided by joules per coulomb. You could actually write it as coulomb squared per joule. But that's kind of ugly, and you could convert joules into something more fundamental as well. But because it's used so frequently in electrical circuits, it's given its own unit. The unit of capacitance is a coulomb per volt, but it's named the farad, named after our friend, the janitor, Michael Faraday. Shortened part of his name. It's abbreviated capital F. 1 farad is 1,000 millifarads, or 1,000,000 microfarads, or a great deal of picofarads. Capacitors are usually written, and if you grab an average capacitor, it's expressed as a certain number of microfarads, picofarads, or even nanofarads. So, going on. Capacitance. Originally, we talked about this as being a farad. It was assumed that a farad would be an impossibly large capacitance. I once asked my university professor, hey, how big would a 1 farad capacitor be? And he laughed at me and said, oh, it would fill this entire lecture hall because you would have to make it huge. Well, things have changed since then. What you see over here is a 500 farad capacitor, and it's only a couple of inches tall. Obviously not the size of a lecture hall. Things have changed dramatically, and we'll talk a little bit more about it later, but now you can actually get capacitances that are easily a farad or even larger. The 500 farad you see here is actually one of the largest ones made right now, but it's reasonably small. It would fit in the palm of your hand. I want to look first at a parallel plate capacitor. It's the simplest of all types of capacitors. It's just 2 parallel metal plates separated by an insulator. You can sort of see it here, area A, and then you separate it by some distance. Usually we call that D. And in this particular case, this one's separated, D is measured this way, and it's separated, the insulator is simply air. And the area would be the cross-sectional area of one of these circular metal plates. It can be circular like this, or it can be rectangular, if you can imagine this being part of a larger rectangular plate, which I did not draw very well. You get the idea, where that area is that. So now the mathematics. If you remember, a charged infinite plate had a certain electric field. Well, first of all, what would the Q be on this one? Let's say it's charged to some sigma. Sigma is how much charge per unit area is on each one of these plates. Then the charge on it would be equal to sigma times A. Next step, calculate electric field. You can use Gauss's law, or in this case, if you remember, we actually calculated the electric field around an infinite plate. If you look back in your notes, you'll see sigma over 2 epsilon naught. That field extends out to infinity. In this case, and I just probably should draw it on here real quick, what do you have here? Well, technically the field lines around this positive one are pointing this way and this way out to infinity. I'm going to draw on here, it's facing this way, and those extend over on this side as well. And the electric field lines from the negatively charged plate are pointing inward. So this negatively charged plate over here, so I didn't draw positive ones in the other one, are pointing this way, and inside of here they'd be pointing this way, and outside of here it'd be pointing this way. And because electric field doesn't depend on distance, if you look at this equation, what is the electric field on the outside of this thing? Well, on the outside, the electric fields cancel, and the electric field here is simply zero. And the electric field on the other side is also zero. They cancel out. But what's the electric field on the inside? If you look closely, they're both pointing in the same direction. This is the electric field due to one plate. What's the net electric field going to be inside of this? It's going to be sigma over epsilon naught due to both the charges on both plates. We're assuming that both plates are charged the same sigma, just one positive, one negative. Like either positive 1 coulomb per square meter or negative 1 coulomb per square meter or something of that sort. We're leaving it all in variables. Once you have the electric field using Gauss's law or previous ones, next thing we have to do is calculate the voltage or electric potential difference. To do that, remember it's just going to be equal to the negative integral of the electric field dot distance. In this case, I'm simply going to integrate. I'm going to define this as 0. Or actually, let's go the other way. Let's start over here at 0 so we end up with nice numbers. And we're going to integrate all the way over here till we get to letter D. So my limits of integration from 0 to D, the electric field is given by this. If we integrate that, sigma and epsilon naught are constants. We can move those outside, and the integral of dx simply becomes x. If we plug in our limits, 0 becomes 0. We plug in d, x becomes d, and you end up with that. I'm sorry I didn't have a chance to write out the limits on this one, but hopefully you can kind of see it. Finally, last step. You're like, wait, this is kind of like when we're doing this one, it's sort of like chapter 24, where we had to calculate electric potential. You got it. And when we did Gauss's law, that was kind of chapter 23 to calculate electric fields. Yeah, this chapter just builds on it. You're like, oh no, I thought we might be finally done with Gauss's law and electric potential. No, we're going to just keep building on it. The good news is the last step does not require calculus. To calculate capacitance, all we have to do is use the definition. In this case, that's the charge per volt. That's the definition of capacitance. What's the charge? Well, from up above here, it's just sigma times our area. And what's the voltage? Well, that's from what we just calculated over here. We can plug that in. And notice I'm only using the magnitude. I'm ignoring the sign. It's the magnitude of the voltage difference. We don't really care about sign. You can't get negative capacitance. And if you solve this, we discover that the capacitance of a parallel plate capacitor is simply given by this equation. And this one, we're going to use a bunch. But notice this bottom part here. Only the geometry of the plates affect the capacitance, not the amount of voltage, not the amount of charge. What happens if you double the area? It will double the capacitance. What happens if you double the distance between the plates? Well, that's going to halve the capacitance. So you can sort of see to maximize capacitance, we need maximum area and the smallest possible distance between it. One last slide on this one. One quick practice one. What's the capacitance of two 1 square meter pieces of aluminum foil that are separated by 0.1 millimeters? All you have to do here is plug into that formula we just had. It's the area of one of the plates. It doesn't matter which one you choose, so you don't plug in 2 here for the area. And 1 millimeter converted to meters is going to be 1/10,000th of a meter. If you divide this out, we simply get 10,000 times epsilon naught, or solving it, we end up with 8.85 times 10 to the negative 8 farads. You kind of get the idea there, pretty straightforward. You could also write that as that many nanofarads. Nano being 10 to the minus 9th, you would just move the decimal point over, 88.5 nanofarads. Is that a large capacitance? Not really. Is that a large chunks of foil? Yeah, it is. So you can sort of see it's difficult to make large capacitances. With that, your homework tonight, it has you actually doing some capacitance calculations. Hopefully it's not too terrible. We'll pick up and do some more capacitance next time. But the parallel plate capacitor is sort of the most basic of all of them. Good luck, and we'll see you soon.